Hey everyone, welcome back. In this video, we're diving into the second objective of this lesson. Specifically, we'll be exploring the linear scheduling method, what it is, how it works, and how you can use it to create an effective project schedule. Let's get started. First, let's discuss how a construction schedule is structured using the linear scheduling method, LSM. The core idea behind LSM is to plot time on the horizontal axis and distance or location on the vertical axis. This approach provides a key advantage over traditional bar charts, which do not display location information, making it harder to visualize where activities take place along the project alignment. Alternatively, you can reverse the axis, placing time on the vertical axis and location on the horizontal axis. However, this setup is less commonly used compared to the standard approach. Now, let's break down how the LSM classifies different types of activities and how they are represented visually. First, we have linear activities. As you learned in the previous video, these are tasks that repeat continuously along the project alignment. In an LSM diagram, they are shown as a diagonal line. The starting point represents both the starting location and the start date, while the end point marks the final location and completion date. Next, we have bar activities. These are tasks that take place at a fixed single point over a certain period, meaning their location doesn't change. On the LSM diagram, bar activities appear as horizontal thick bars. The length of the bar represents the time span from the start date to the finish date, while its position on the y-axis remains fixed. Another type is the block activity. These tasks require a large working space and extend over a long distance along the project alignment. However, unlike linear activities, they are not continuously repeated. In the LSM diagram, they are represented as rectangles that show both the time span and the spatial area they occupy. Finally, we have milestones. These represent major deadlines or key events in the project. In LSM diagrams, milestones are shown as diamonds. On the x-axis, they are positioned at a specific point in time, and on the y-axis, they are usually placed at the final location of the last activity that needs to be completed before that milestone. Alright, let's take a look at how the Gantt chart for our tunnel project translates into a linear scheduling. You may remember this Gantt chart from the previous video. Now, using LSM, it transforms into this visual representation. Let's zoom in and break it down. First, we have two site preparation activities, shown in orange. These occur at two fixed locations, the south shaft, Station 10, and the north shaft, Station 110. Since they happen at specific points, rather than along a continuous path, they are represented as bar activities on the LSM diagram. Similarly, we have shaft construction activities, marked in blue. These are also bar activities because their locations remain fixed. While shaft construction at both sites follows a similar process, they are separate activities occurring at different locations. That means they should be treated as two distinct bar activities, not one continuous task. Next, we have the tunnel excavation activity, which is a linear activity. It progresses continuously from the south shaft to the north shaft. Looking at the timeline, this activity spans from the first quarter of 2018 to the first quarter of 2019. The only box activity in this project is the punch list, which takes 1 quarter to complete. It is represented as a rectangle because the final corrections in the punch list happen across the entire project area, from the south shaft to the north shaft. Finally, we have the substantial completion milestone, shown as a diamond. This milestone is positioned at the end of the third quarter of 2019 and marks the completion of work at the final project location, the north shaft. By mapping these activities on an LSM diagram, we can clearly see how different tasks are scheduled and how they interact over time and space. Alright, is there more information you can gather from a linear schedule beyond just time and location? Absolutely. A linear schedule provides valuable insights for managing linear projects effectively. One key piece of information is production rate. The slope of a linear activity line represents how fast work is being completed, essentially the rate of production. In linear projects, production is often measured as distance per unit of time. The steeper the slope, the faster the activity is being completed. If you notice a change in the slope, that means the production rate has changed during the project. For example, right here, the slope is steeper, so there could be favorable conditions that help increase the production rate. Or, a sudden flattening or a gap in the line, like this period, will indicate a work interruption. If the distance doesn't change over that period, it means no progress was made. By analyzing these slopes, you can spot issues early, such as slowdowns or interruptions. As a project manager, this information helps you identify problems and take action to keep the project on track and avoid delays. Another important piece of information you can extract from a linear schedule is the distance buffer, which refers to the physical distance between activities at a specific point in time. To better understand this, let's look at an example from a highway project. In this case, we have two activities, excavation and subbase, both beginning at Station 0 and ending at Station 1 and 10. However, excavation starts first at an earlier time, while the subbase work begins later. This delay may be due to technical or space constraints. At the beginning of the project, before the subbase activity starts at time t0 OS, only excavation is taking place. Once subbase work begins, both activities are happening at the same time, but at different locations. Since excavation started earlier, it moves ahead of the subbase crew, creating a distance buffer between the two activities. Later, once excavation reaches Station 110, only the subbase activity remains. So, basically, by reading the linear schedule, you can determine where each activity is located at any given time, and also measure the physical distance between them along the project alignment. To find this distance buffer at a specific moment, you can follow this simple approach. First, identify the time you're interested in, and draw a vertical line at that point on the schedule. Then, note where this line intersects both the excavation and subbase activity lines. Next, project these intersection points onto the vertical axis, which represents location, to determine the exact positions of both activities. Finally, the difference between these two locations gives you the distance buffer, or the space separating the two activities at that specific time. It is important to remember that you can only measure the distance buffer when both activities are occurring simultaneously. If excavation finishes before subbase work begins, or if subbase has not yet started, there is no distance buffer to calculate. Now, you might wonder, why is this measurement so important? The answer lies in how construction projects are managed. Imagine you decide to speed up the subbase work to reduce the overall project duration. As a result, the subbase crew will move closer to the excavation team, narrowing the distance buffer. However, if these teams get too close, they may run into logistical challenges, such as limited working space or inefficient resource allocation. In practice, construction projects often require a minimum distance buffer between activities to ensure smooth operations. If this buffer becomes too small, worksite congestion can lead to delays, inefficiencies, and safety concerns. That is why measuring and managing the distance buffer is a critical part of keeping linear construction projects on track. One more crucial aspect to manage in linear projects is the time buffer, which refers to the time delay between two activities at a specific location. For example, at Station 0, the starting point of the project, the time buffer between the start of excavation and subbase is simply the delay in their start dates. Meanwhile, at the endpoint, Station 110, the time buffer is the delay in their completion times. As you move along the project alignment, the time buffer changes, and in this case, it gradually increases as you approach the project's endpoint. To measure the time buffer at a specific location, start by identifying the location of interest, L. From this point, draw a horizontal line until it intersects both activity lines. Next, note the intersection points and project them onto the time axis. The difference between these two time points represents the time buffer at that location. Just like the distance buffer, the time buffer must meet a minimum required value to ensure there is sufficient lag time between activities. Maintaining this buffer helps prevent scheduling conflicts and ensures a smooth workflow throughout the project. When developing a linear schedule, it is crucial to avoid interference or conflicts. These occur when a succeeding activity starts too soon, without enough buffer time, causing it to catch up to the preceding activity and creating a scheduling conflict. To resolve this issue, you can adjust the schedule by shifting the second activity, in this case, the subbase activity, represented by the red line, to the right until there is no overlap between the two activities. Alright, that's it for this video. We covered how to set up a linear schedule, how to represent different types of activities, and how to interpret the schedule to identify potential issues. Thanks for watching, and we'll see you in the next video. Goodbye.